Good afternoon, and thank you for joining us on our call today. My name is Nicole Van Wert Quincy from Transcat, and I'll be your moderator this afternoon. Our webinar topic today is an introduction to temperature measurement and calibration. The topic is being presented by Travis Porter from Fluke Calibration. Travis has been with Fluke Calibration for 20 years and has served in a variety of roles, including manufacturing, technical support manager, and his current role of inside sales account manager. We expect the presentation today to last roughly 30 minutes, and then we'll open it up for questions and answers at the end. During any time during the presentation, you can send questions through the question box, which is in the right side in your webinar controls. I also want to mention that the webinar is being recorded. You will each receive a follow-up email with a link to the recorded webinar and the slides of today's presentation. And at this time, I'm going to turn the presentation over to Travis.
All right, welcome everyone. I hope this is useful. So again, as Nicole mentioned, if you do have questions along the way, please put them in the text or the chat box, and we'll get to them at the end of the seminar. So again, today is an introduction to temperature measurement and calibration. Hopefully it gives you kind of a good overview for those that may be getting started in the industry. So again, there's a lot of things we'll cover, but again, some of the basics is, what is a good heat source? What are the different types, different probes? What are some best practices? What's a good calibration, recalibration intervals, things like that. So again, as we go through this, please keep those questions coming. We can have a good discussion at the end. As Nicole mentioned, I've been in the industry about 20 years. Started in 1999, so again, had a few different roles over the years. Currently, I'm inside account sales manager, specifically for temperature calibration. With that, let's jump into it. So again, this is an introduction to temperature measurement and calibration. So we're gonna go over calibration methods, kind of product choice, or how to pick what's appropriate for my application. We'll also go into some of the best practices, such as placement in your heat sources and reference thermometers. So again, some of the high level overview. Again, we're not going to dig too deep into uncertainty or accuracy, more or less just a quick overview of getting kind of a good foot in the water on what where to start. So there's two main types of calibration methods. One is called comparison. So that's usually in something else. So you're comparing to something else. And then we've all have what we call fixed point calibration. Fixed points are kind of at the top of the pyramid as far as the precision goes. They're also used worldwide. So basically, when you've plateaued a fixed point cell, these can be reproduced almost anywhere in the world and to the same known. So again, that's why they're kind of the critical piece, kind of the top of the pyramid, where we use those to calibrate SPRTs, and from there the SPRTs kind of propagate down through the different applications and different sensor calibrations. So here's just a quick overview of the pyramid I was briefly mentioning. So it's basically showing fixed point cells to industrial. So if we go top left and then right, back to left, right, basically you start out with your fixed point cells. Those are used to calibrate SPRTs. Typically SPRTs are then used in a bath or secondary heat source to calibrate PRTs. PRTs are then used to calibrate industrial heat sources, which can also be baths as well, but here we've got the dry wells pictured. And then from there, you kind of come across where those are used to test and validate different industrial sensors. So as you see here on the left, and there's a line through it, but you kind of keep ramping up in uncertainty as you go down in the pyramid. Again, that's just, you lose a little bit each time you kind of go down a level. So again, the intrinsic standards of the fixed point cells are where you kind of start with the entire calibration process. So for a fixed point cell calibration, and if you want more information on this, you can go out and Google ITS-90. That'll show all the fixed points that are in place and used. There's a variety of what they call sub-ranges, basically 1 through I think 11, and these are different fixed point cells that you gather data or points you use to kind of create a known curve fit for different SPRTs or ranges of temperature. But for fixed point calibration work, again, this is just kind of, there's more than just one piece that go into it. You can't just have a fixed point cell and you're good to go. Most of them require a maintenance apparatus. This can be a furnace, a bath. So for some of the lower temperature stuff, it's baths are used, like for the triple point of mercury. You've got to cool it down to about -38, -40 to make it happen. And then once you achieve your plateau, you've got to have a way of transfer. So you've got your SPRT and then a really good thermometer or bridge to kind of take that resistance reading. One thing that's not shown here that's done at this level as well is usually when metrologists are working through a fixed point process, they also have another secondary SPRT that kind of follows the devices they're testing, or the new SPRTs, and they call that a check standard. So again, they're basically making sure, you know, that something doesn't go awry during the plateau process in the fixed point. With the fixed point process, you can achieve a very, very low uncertainties in the cell. Some of them are as low as 0.15 millik. So again, when you hear that, that's, you know, 0.00015 is what you can achieve in some of the fixed points. So very good to start, you know, the calibration chain, or what they call a traceability. So again, going back to kind of the discussion, you've got to have the standards, or I should say the fixed point cells become your reference standards, but then again, you've got to have your temperature source to maintain this cell, and then also a good way to get that data out of the cell so again, it takes a few different pieces. There's also pieces that people don't realize on the maintenance side for maintaining the fixed points. So that's a good discussion if you're looking to get into this. So again, with some of these furnace heat sources, you do have to have separate probes in that you're using to profile the furnace and set the cell up to make sure that you don't inadvertently break it or cause a gradient that can give you some problems down the road. So once you jump past the fixed point cell, you get kind of down into the comparison. Again, kind of the same mythology. You're going to have a reference standard now. So typically, you're going to have some sort of a probe, can be an SPRT as your reference, or if you're in a dry well, you know, maybe a little bit more of an industrial grade. But then you're also going to have your temperature source that's going to be more so responsible for your stability, uniformity, and the heat. And then also you got to connect your probe to some sort of a digital readout to interpret that resistance that it's off-putting to temperature. So now you have three pieces, basically a probe, a readout, and heat source working in conjunction to provide you a known, stable heat source that you can put other devices under test in and get the respective resistance or temperature out of. So in this first example, it's kind of a calibration example of, say, an industrial sensor that you're just calibrating directly in a dry well. So again, in here, you're going to be calibrating directly to the control sensor of the dry well. And depending upon the dry well type and range, dry wells can go anywhere from, you know, a half a degree or better. Sometimes you get down to 0.2, 0.1 on the display accuracy. So again, we'll touch on this a little bit further, but again, depending on what you're testing, most folks will typically try to hold to a 4-to-1 type uncertainty. So most, again, processes will require to be some level better. And again, in the industry, it's typically 4 times better is very common than whatever you're calibrating. So in this example, let's assume that the dry well is, you know, 0.25 degrees C accurate to the control sensor. So again, the unit you're testing would probably have a spec close to ±1 or greater, and that would be appropriate. So again, in this example, you can see the unit in test and the control sensor. Again, we're trying to align them up very closely and then reference to the display. The next kind of jump in a heat source and a reference, instead of calibrating just to the display, is adding a reference. In this particular example here, we've got a transmitter head, potentially with, say, a thermocouple with a 4 to 20 milliamp circuit on it plugged in. And then here, this particular dry well in use has a built-in reference, readout function, and probe. So again, here, that allows us a kind of a one-up. So again, instead of relying on the internal control sensor of the dry well, we're now kind of bumping up to an external probe that's going to have a much higher level of calibration or lower uncertainty. So again, you're building upon your overall uncertainty. So again, instead of calling the display true temperature, now we're going to call the reference temperature true temperature. The display then becomes kind of like your nominal set point. So again, just building on the next step. And then kind of building on another comparison calibration example is moving from, say, a dry well to a bath. Baths typically are used when more stability is needed and uniformity. This allows for more throughput. And the reason for that is typically the fluid volume allows for this. So again, when you're kind of investigating a bath versus a dry well, we'll touch on those as we continue on. But again, in this particular example, you can see here we've got multiple devices under test, assumably probably secondary or higher end probes being compared to an SPRT, you know, with basically a multiplexer and then the reference. So again, for manufacturing purposes or customers in commercial labs that may be doing higher volumes, baths are typically utilized versus a dry well, which may be more suited for a factory floor or a quick check or field use. Just a little more easy to transport, throw them in the car, the truck, or a cart and get them around the factory. So again, things to consider there in the process. So again, jumping to that question, you know, you've got to consider what types of sensors am I calibrating, or where do we fall within that level of uncertainty in the pyramid? Are there any considerations I need to think about? Like, are my sensors long, short, big, small? How much accuracy am I going to need? What is the temperature range I'm calibrating over? So again, with that accuracy need, again, in the industry, and it's again, been 4 to 1 as long as I've been around, kind of on, not related to temperature, but some of the other disciplines, the devices or equipment that you're using, the technology is kind of progressing. So we're seeing on that end, or different, potentially in electrical and pressure, sometimes you can't maintain a 4 to 1 because the actual standards don't have that capability. So sometimes it's brought down to a 3 to 1 or 2 to 1, just because technology is progressing well on that side of the fence. But again, for temperature, usually it's 4 to 1, or you have to kind of disclose an overall uncertainty of the calibration. So again, things to remember there, people get hung up on accuracy, tolerance, uncertainty. Accuracy and tolerance of the device you're testing typically means, you know, how good it should be. Uncertainty is how well I can measure that at a known. So again, sometimes folks can kind of get kind of caught up in some of those different terminologies. You get uncertainty and accuracy. You know, people try to use them interchangeably, but reality is they're not. So again, things to be aware of there. So this is just another slide. Again, not much to look at, but just kind of showing the different types of sensors here on the far left as a workload of what you may be tasked with calibrating. You know, I see a lot of folks with dial thermometers, liquid and glass, your industrial grade RTDs, or maybe a slightly better PRT, thermocouples, thermistors, SPRTs. And then, you know, we're asking, where am I going to calibrate these, or what do I need to do? So again, we've got a kind of a variety. Dial thermometers, a lot of folks will calibrate them on site. They're used in big walk-in refrigerators or different things like that. Liquid and glass can be done in a laboratory. Again, it's kind of a real mixed bag. This was just kind of example. Again, it's not anything that, oh, I've got liquid and glass, so therefore they're only used in a laboratory. Again, it's just kind of asking the questions or things that you should consider regarding what I need to do and where do I need to do it, or what would be the most appropriate. So again, with each one, again, you can see kind of on the equipment needed. Sometimes it's a simple one piece. You know, I can do this with a drywall or a bath that's got a good calibrated actually to the display. Other pieces, you see, you're going to need multiple pieces of equipment and you know, multiple processes to kind of make the calibration as a whole happen. So again, kind of just showing a variety of things there to consider. The next biggest one I come up against are shapes of sensors. So in the industry, a lot of folks just make the sensors and then another manufacturer will take that sensor and then embed it into their design there. I've seen these, you know, come in very large diameters, very short, high temp, low temp. The hardest one I still come up against today is very short sensors that are capable of making very high temperatures. Those become very difficult because it's kind of hard to get a good overall heat source reference and everything set up where you only have, say, 2 or 3 inches of immersion. So again, a lot of times what happens with some of these sensors is the calibration of the actual sensing element is kind of predetermined before it's built into the actual housing of the sensor, which kind of poses the problem that I spoke to there after the fact, because you're kind of stuck now with this housing. And again, you're limited to a dry well or a bath, and maybe it's outside the temperatures that you could achieve, and you need to get a big furnace involved. But now I need, you know, 12 inches of immersion, but I've only got 3 inches of a probe. So again, there's challenges there based on the shapes of sensors. Typically, for short or uniquely shaped sensors, a bath is a better option. It just provides a lot more flexibility, and you're going to get a lot more thermal conductivity with the fluid versus in this picture here, you can see kind of more a traditional PRT probe that typically they're an 1/8 or 3/16 or a 1/4 inch diameter and sheathed anywhere from, you know, 6 to 12 inches is really the most common. So again, things to think of there. What the biggest I guess thing that comes into play with the sizing is the immersion, and typically on a standard probe like that one in the middle, there's a consideration for stem conduction, so where the actual metal acts as a heat source or a heat sink, I should say, in the application. So again, the rule of thumb there in the industry for a immersion depth is typically 20 times the diameter of whatever the stem is of the probe. So again, how much calibration accuracy is needed? Again, as I've talked to a couple times so far, TR is usually 4 to 1. So in this example here, we're going to assume we're calibrating a typical RTD. It's 100 ohm, or yeah, a DIN class A, so it's going to be 100 ohm at 100 C. So we should be getting approximately 138-ish ohms out, and that correlates to about, you know, the 100 degrees C for that. And we're trying to calibrate it to 0.113 or ohms, which correlates to 0.35 C. So in that 4 to 1, we're going to take that 3.5 divided by 4. So our heat source, stability, uniformity, reference standard, and reference readout all needs to culminate to 0.0875 or better in order to achieve that 4 to 1 ratio, you know, that we were looking to keep in this process for the DIN class A. As we've gone through, we've kind of, you know, seen a few different pieces between baths, dry wells, different probes, and I say, well, why is this the range important? Again, it's just, again, the sensor types. There's such a wide variety, ranging from your base metal TCs to precision TCs or special limits of air, loads of different RTD types. You've got typically your DIN class A, B, 1/10 DIN, 1/3 DIN, and then you've got the ones that are very specific, like we sell, that are calibrated to ITS 90. So again, given how they're built up, they'll have different sheath lengths and stems, and that all plays into the capability of how they can be used. So again, some of the more common applications I come up against or sell into are like these big walk-in freezers or smaller cryo freezers, freeze drying units, blood banks, washers, disinfectors, incubators, autoclaves. Again, it's just a very wide variety, all the way up to you get into some of the industrial automation or heat treating processes for aerospace, or the control feedback loops that are used in jet engines or just engines in general. Again, those applications go upward of that 1000 C. So again, depending on how these are used, it's kind of how you have to kind of start that questioning process. How am I going to test and get a known and get good results based on what the end use application is? So again, a lot of times with the temperature side, again, it's really a lot of times I have to read. There's a lot of read in between the lines based on what you are looking to achieve and what can be achieved and what would be considered a best practice. So in choosing kind of a sensor or something that's a reference for a process, we're going to keep this pretty simple here. You've got your thermistors. Typically these are very accurate, but over a very small range. And we've got several different designs. Some are designed like your more traditional probes that are just a stem, where the stem can be exposed to the temperature. And we also have some that are full immersion. So again, depending upon the application where it's going to be used, that's kind of that read in between the line piece of the process that has to happen. Kind of the next jump down are your more typical RTDs or PRTs, where you see the more traditional sheath lengths. These ones tend to have a higher accuracy, slightly higher cost, but again, a variety there. The most common ones we've talked about, like more industrial here, of 100 ohm RTD or a DIN class A RTD, or a 385 RTD or 392. These are all just references to the types of platinum that are used, their curve fit, whether it's a generic or very specific. So again, it's getting familiar with what you're calibrating. And again, usually if you're calibrating something like a PRT, you're going to want to be using the reference equipment at that next level in that pyramid that we initially shown to kind of build that uncertainty that you'll need. And then we move kind of into the really high temp stuff, of which is usually TCs. Most PRTs are limited to about 400 to 500 C. We do have a few models that can take some heat up to like 660, and I've even got one that'll go to 1,000. But once you kind of range outside of that, you kind of have to go back to the thermocouples. And again, where we've got thermistors, very high accuracy, very small range. As you give up kind of some of the range, or you need more range, you kind of lose some of your accuracy. And again, that's just due to the physics of things. When things are being exposed to such high temperatures and cooling and heating, if we get into the weeds, basically the crystals of the metal are moving so quickly and changing states. That's where you see these drift across the different types of probes and sensors. Now, once you have your sensor, you're obviously going to need something to interpret the outputted millivoltage or resistance, to interpret it into temperature. So again, as we kind of go across this chart, depending on what you're doing, again, that's kind of the in between the lines. Am I using this in the field? Am I taking it out with me? Is it just for lab use? We've got a wide variety of things that you could consider that are very portable. Some have higher capacity, some are quicker. Then again, we've got some of our heat sources with built-in references. So we've got that multiple faceted tool that kind of allows you for that all-in-one type use. So again, when you're picking things, it's always good to have a good discussion with the person you're buying the equipment from, and kind of talk through everything you're looking to accomplish and what you'll be coming up against. And as we kind of move to that, so now we've got our probe, our readout, now we've got to look at a heat source. So now that we can measure, how are we going to create a nice uniform temperature to measure and put our devices in? So again, as we talked at the top of the pyramid, you've got the ITS-90 or the fixed point cells, which is kind of the way the world has said, yeah, this is what we're agreeing to is temperature. Then you move through into your variety of different baths that uses different types of fluid, anywhere from ethanols to silicone oils to salts for the very hot stuff. And then you start moving into your variety of different lab grade wells, field wells, and then your lab grade or more industrial smaller baths that you could use. Again, depending on what you're doing, do I need portability or I need throughput? These are all things to consider, or if I need automation, am I looking at a all-in-one solution? Again, talk it through, the process, what you're looking to do, what you may need to do at a different date or different application, and just kind of think it all the way through on that. So we had the first slide where I gave you that calibration example of the unit being calibrated in the dry well just to the display. And we kind of showed the placement there of the internal sensor and the unit being tested. So the idea is, getting your sensors kind of closely aligned so you get a good reading so that, the uniformity and stability of the bath, or I guess it would be more or less the uniformity is going to be lessened. So again, if you think of a bath uniformity, that's kind of taking the whole volume of the bath and saying, well, if I have a sensor in the top right and bottom left, one in the middle, there's going to be this air. So there's a way to reduce that by kind of pushing everything close together within the same space, and then putting your reference there in the center. And that kind of gives you a better way to kind of reduce that uncertainty of the top, bottom, middle placement that's done in kind of the R&D side and the specification of the bath. So it can improve actually that uncertainty spec quite a bit. Some folks will also, because of the fluid, they'll add what they call lag blocks to kind of add some additional mass. So again, it's just a block of metal, kind of like a dry well insert into the bath that allows, again, for some more thermal mass. That you add mass, slower to change to fluctuations in baths. So again, there's workarounds depending upon what you're doing. And again, brought this picture back up again just to show you here. If we go between these two, you can kind of see, ideally here, we've got the 4 sensors that we're testing and then the reference in the center. Ideally here, this was just to kind of show you throughput. But if we were actually calibrating these sensors, we would probably have this reference in the center and then potentially a circle of these devices that are test, basically not side by side going across the bath. So again, trying to reduce that space that we're utilizing to kind of improve upon the uniformity spec. So that's just a little tip there. And again, with the dry wells, again, fit is key. So if you have an 1/8" probe, you don't want to put it into a 1/4" hole. You want to match it as best you can. Typically, for example, if where you have a 1/4" probe that's 5, the 1/4" hole that you're inserting to, or that would be considered the proper placement, is usually drilled about plus 0.015 bigger. So again, it's a tight fit that allows just enough for really good thermal conductivity, but not tight enough that as things expand, it's going to get stuck. So again, there's kind of that happy medium that it's got to still fit as we increase in temperature and things swell a little bit, but we don't want it to get stuck. And again, too, ideally, if you're placing on that picture on the right, you want to immerse your sensors at the same level, so you're aligning basically your reference sensor and the device under test sensor. I didn't include a third picture here, but this would also be appropriate if, say, you had a shorter probe and you could immerse, say, your reference, not all the way to the bottom, but say up 2 inches, and then say your device you're testing doesn't quite meet the bottom, it's 2 inches short, you could align them that way. And that would also be an appropriate way of getting them, again, helping to kind of reduce that uniformity or gradient errors that you do run up against in some of the heat sources. All right, so now that we've kind of talked through a few things, maintaining your standards. So that's usually more of a consideration for your probes and your readouts. As we've talked with some of the higher end probes, RTDs, PRTs, they are platinum winding. They do drift through normal use, so just time and use makes them drift. Also, physical vibrations, bumps, taps, or like a motor vibrating or tapping, that's going to make them drift quicker. So again, shipping, things like that, make sure you package them well if you're sending them out for service. You're going to want to calibrate at regular intervals, but you're also, one thing people don't tend to do is kind of monitor in between calibration cycles. Unfortunately, once you send something out and a Cal Lab receives it and they recalibrate it, they can only report on what it's doing right now. If there was a bump or something that is going to cause you an out of tolerance that say happened 6 months ago, there's no way for a lab to tell that. They can only report on what it's doing right now. The best method to kind of prevent that, well, the best method is a triple point of water, but you can also use like a really ice bath in a dewar. This is just really good, cheap insurance to write into any QA process that you're going to check your standard at 0 periodically. And again, this is going to have to be defined by your quality folks typically, and it's usually a result of risk versus recall. And again, trying to negate that. So this one shows a triple point of water. They're going to get you the best repeatability, but again, a good made ice bath in a dewar also nets you really good uncertainties. If they're built properly with distilled water, distilled ice, you crush it well and allow it to stabilize. They work really good. And again, really cheap insurance to take a few minutes every few weeks to check your unit. So again, what you're going to do typically with your control chart, this one is done in temperature. This one was done in resistance. So again, with the resistance side here, basically you take the difference in the resistance versus the reading you're getting from when you started, and you can kind of take the difference between those, and if it's a 25 ohm probe, you divide by 0.1. If it's a 100 ohm probe, you divide by 0.4, and that gives you a rough approximation of shift in degree C. Or again, you can just do it in temperature and watch your drift, in temperature. So we're going to talk to the triple point. Again, really good, cheap insurance. Again, triple points are used. That's probably the most common fixed point used worldwide. They're relatively inexpensive compared to other fixed point cells. They're not as difficult to maintain or use, but you can typically get in the realm of like it's like 0.0005 C repeatability when you're using one of these. So again, a really stable, easy way to repeat that check. But again, you can also do an ice bath if it's built and maintained properly. The uncertainty will be slightly higher, but again, still good, cheap insurance. Other things too that I've ran across over the years is people not being familiar with the equipment. So education is key on how to handle them, store, transport, training your people, and then the monitoring, again, is that another piece I've seen customers fall short on when I was on the technical side. So I get some complaint, they send in a probe for Cal, it fails, send it back, hey, this is out of tolerance, and then they come back, well, when? And again, that's something we can't determine unless you're monitoring it constantly throughout the Cal, between Cal cycles, I should say. All right. So this is kind of a close-up of an SPRT of what shorted or I want to say strain sensors can potentially look like. We did this on an SPRT model. So again, these are really zoomed up. But again, you can see the different little coils, but what happens with the shock or vibration, it can totally dislodge the coils, or it can cause them to touch. That causes your resistance values to go up. So again, those ones there really took some hits. You can see there where they've touched, or this one actually dislodged from its winding groove on the far left there. RTD sensors, they don't have this same design as what they call a strain-free design. They kind of have something similar, but they're potted, but they still don't take to physical shock kindly. They will drift because of it. So again, handling it is key. So again, just a fun comic here to hear something, and that's your probes going out of tolerance. But that's about all I've got for now. I hope this was kind of a good starting point for you that are considering getting into some temperature measurement. I think we're open now to some questions, and we'll take it back to Nicole.
Okay, everyone, thanks. That's it for our presentation portion of the webinar, and we are going to go into the questions section. If anyone does have questions, please submit them through the webinar box, the question box in your webinar controls. All right, I'm going to go to the first question. Why would I use a reference instead of the bath display?
So with the internal control probes, they're usually an industrial grade sensor, and while we can calibrate them to a fairly decent uncertainty, they're not as good as an actual probe that's been calibrated, is made from a higher grade. So again, most baths, you're going to see anywhere from a 0.5 degree to 1 degree on their display accuracy. Dry wells vary from that to as good as maybe like 0.1 or maybe even an 0.5. But a good reference allows you to kind of go beyond that spec as a reference.
All right, how critical is it to match immersion depths of probes?
Very, very critical. So again, this was kind of that challenge I spoke of in the beginning, where you have some short sensors. So again, there's a couple of things in play there with the immersion. Is the stem conduction is one. So again, matching that. So again, for your standard being used, you have to get immersion to negate your stem conduction, but you also then need to match your device under test. And again, what that does is it puts you in closer proximity to the device under test and what's being referenced as true temperature.
Okay, why would I choose a bath over a dry well?
There could be a couple reasons. Most of the time with a bath, it nets you overall, if you're using it with another external reference, it nets you more stability and uniformity, so you can kind of get a lower overall uncertainty in the process. Baths are also useful if you've got, again, very short or very odd shaped sensors, because again, you're going to get that nice heat transfer via the fluid versus a dry well that are more traditionally designed around a typical just straight type style probe or sensor.
All right, what are the coldest and hottest temperatures you can achieve using a bath?
On a bath, I've got them that'll go minus 80 in a fluid. We used to get down to about minus 100. We do have a dry well that'll do minus 95 C. But on the very, very hot end, that's where you kind of move past your silicone oils and move into like a salt bath, where it's molten salt, and you can run those as hot as 550 C.
Okay, that's it for our questions. Travis, if you go to the next slide, it has my contact information on it, so everyone can see that. And so everyone, thank you for attending. It concludes our time for today. If you have further questions, or you would like to find out more about Transcat's product and service offerings, please contact us at 800-828-1470 on the web at transcat.com, or you can email me directly at mfanward@transcat.com. Thank you for joining us today. We hope you got something out of the presentation and that you can continue to join us for future Transcat e-learning webinars. Thanks, everyone, and happy holidays.